Dear colleagues, it is time to begin our session. I'm happy to welcome you at 7th International Congress of Energy Fluxes and Radiation Effects. And my name is Yakovlev Igor, and I'm researcher of Tomsk Scientific Center, and I will be a chairman of our session that is devoted to topic combustion waves, theory and experiment. First of all, as we use the online format, I want to remember you that we may have some technical problems, and please be patient about that, and remember that due to limited connection, some delay occur, and don't hurry up. After speaker invitation, one should click a green button, go on air, and make presentation. You can use keys left and right on UK keyboard to switch slides. Right during the talk, you can type questions on the chat, and after the talk, I will voice new questions. And we also have a time limit for speakers. It is 15 minutes for presentation and 20 minutes for invited presentations. Please follow the rules. Let's start. First speaker is Dr. Vyacheslav Bykov, and please start your presentation.
Thank you, Chairman, for presenting me. So I'm not sure whether I'm really on air and everything is going on correctly. Could you confirm that everything is okay? Somebody? Okay. I just start immediately. So then, good morning, actually, good afternoon and good evening for those that joined from the Far East. My name is Vyacheslav Bykov, and today I'm going to present the result of the mutual work of myself, Vladimir Gubernov from Lebedev Physical Institute from Moscow, Ulrich Maas, and our one PhD student, Sudhi Shidharan, and the master student, Etele Pershani. So what I'm going to present, I will be talking about the rich premixed hydrogen air flames, so that like we have a flat flame propagating into the rich premixed hydrogen air mixture, and after some critical parameters reached, it becomes unstable and becomes some oscillations, different type of oscillations appears, and the problems of detailed modeling of chemical kinetics to catch this event, and also the model reduction are actually in the focus of my presentation. So now I would like to switch the slide. How should I go to the next one? Left and right, they do not work somehow. They do, but probably with some delay. So to motivate, I need to say several words about motivation. Actually, the thermal diffusion instabilities, some very known phenomena. It appears when the Lewis numbers, the diffusion coefficients are quite different for different species, for instance, while within the flame front, are also different to those of the thermal of the heat conduction or heat diffusion. And then they actually appears, they quite well documented, or qualitative theory existed, and when such phenomena appears, then different dissipative structures built up on the flame front, like radial, some drumhead mode, some mixed mode, even chaotic pulsation might appear on the flame front propagating, and also some spiral structure. As I said, there are theoretical predictions, and also this problem actually is very well studied. Why then we are actually focusing on that? So to show that, To explain that, I would say this is one of the objectives of my presentation. Now I need the previous one. So just taking some time as I see. I'm sorry for those confusion because I need to count for those delays with switching back and forth. Oh. Okay, if somebody can help me, I would be happy because it doesn't react. So I would like to go to the third one. Yes, thank you very much. So what we observed, we recently modeled this phenomena with one-dimensional model. What does it mean? It means that those spiral structures, very complicated geometrical properties of the flame front, but the very first mode, the bulk oscillation, can be actually modeled within one-dimensional configuration. And these stability losses and so on and so forth can be already quantitatively predicted using the one-dimensional model that opened the perspective using detailed model and also detailed transport model, and then computationally it becomes very actually we can handle that and compute it very efficiently in a reasonable time. So that's why we concentrated on this phenomena and we focused on the possibility to check and also to verify the chemical mechanisms, chemical kinetic mechanisms, also diffusion models, because we do see and we have this experimentally observed and very well documented phenomena. We can just evaluate on the spiral structure, for instance, how the frequencies of the oscillation should look like and so on and so forth. And this information can be directly compared with the result of computation. And this, as I said, opened the perspective to validate the additionally detailed kinetic models. Therefore, we concentrated and we studied this. Now I'm going to the next one. We decided to focus on this phenomenon. So what is actually happening here? The results are transparently several slides showing what is happening. So if we fix the initial temperature equivalence ratio and also try to increase the pressure, at some point we see on the left slide here, right? On some point, the flame velocity shown by the y-axis goes almost constant, but it actually reduces a bit. But at some critical pressure, the Hopf bifurcation appears, and the flame becomes oscillating, as it is shown on the right slide, where we see the flame oscillating, and also the OH profiles on the maximum value of the OH profile along those oscillation in time. So we see that spikes are actually shifted, and then for different species we do see the spike because at different flame prone position, the different species, they react differently on those instabilities and so on and so forth. But within the detailed models in computation, we have an access to those fine flame front structure. We can resolve it and we can actually decide and study the different models different kinetic models within this phenomena. So the next slide shows the fifth one. It shows the structure, how the oscillations look like. Once we see on the left side where the OH was a minimal value, we see that the reaction slows down, the temperature drops down as well. We see the red curve show the temperature, and when the temperature within the flame front reaches the maximal values, right, we have this value of the temperature. Then the OH concentration peaks at the end. This becomes repeatedly and very regular oscillation structures appears with some certain frequencies and amplitudes, and all those parameters can be used additionally to the, let's say, flame speeds or to the ignition delay times to validate and verify the detailed mechanisms. I'm going to slide next one, the 6. Yes, so to model that, the big actually question is to how to accurately predict those oscillations, especially if I mentioned, or like if I've shown but I forgot to mention, the detailed model to be useful and to be like applicable to the wide range of parameters. They become complicated. Even this for the hydrogen case, it is already about 10 species and about 20, 40 reactions need to be considered. This actually increases the system dimension, the internal system dimension in this chemical state space, so-called, where we do have two hydrodynamic, like enthalpy and pressure parameters, and then we have, like here shown, the mass fraction divided by mole number. The specific mole numbers, they actually describe the composition of the mixture. To describe correctly the composition, thermodynamical properties of the mixture, and also how it reacts, becomes an issue, and we do need to resolve all those scalars for the state space to actually model those ones. Especially if you look at the next slide, in the case when we do have right now a lot of different chemical reacting detailed model. At the moment, we do have about 20 mechanisms, as is shown in this paper of the Varga et al. He compared all those mechanisms for different experiments. It's quite a nice study, but it shows the complexity. We have a different mechanism. So like it is like on the market. We have a different kind of coffee, whatever, and this way actually is a bit counterproductive in my case, but we deal with what we do have actually. Of course, within those 20 mechanisms, actually 2, 3, actually we think that about 5, maybe at most 5, they have a different roots, like very similar and but different roots, and then they merge and they diverge and become more and more complicated. But in the basis, the most important steps are, I would say, might be different only within subgroup of 5 or whatever, 4 original mechanisms that actually initially originated at different schools for about 50, 60 years ago. As a transparent example for that, we compare reaction rate parameters for this very well established actual reaction, and we see, if we consider different O'Connell, ALTE, GRI, Karamis, and so like those are names, the shortcuts of those mechanisms. Even for such a reaction that is one of the, like what it is called, radical propagation reaction, we do see the scatter of the parameter of the frequency factors of the exponent, temperature exponent, and also activation energy. They vary within the activation energy, not that much, but for other parameters, they are quite varies quite substantially. So the question now, how to deal with that? What would be the best mechanism to address, for instance, phenomena we study, or those that are connected to the transition and the transient behavior? This is the crucial point. So the next slide, please. Therefore, we decided to use a couple of mechanisms and compare these performance within the suggested structure. But nevertheless, as I said, although the mechanisms, also certain reactions are different because they focus on the same phenomena, they need to be, how to say, they had to advance, they had to be some, like, they had to describe some invariant property of this reaction, and this is indeed happens. So like the basic properties they address quite well, and they behave similarly as it is shown, for instance, for the homogeneous reactor, for this 150 K initial temperatures stoichiometric. If we just trace and look at the time histories, we do see and we notice they actually behave quite similarly. It is not like a wonder, because they all address the same as should be accurate for certain, specifically for these stoichiometric mixtures and so on and so forth. Why do we go from the let's say the standard experimental setups, a standard mixture composition? The more differences appears, but this is the reason why actually they are different. So the next slide shows the precisely, I would guess, the should be the objectives, yes, of the presentation. As I said, the sensitivity of the flame flow dynamics, how to reproduce this phenomena, how detailed, how accurate detailed models should be, and to have a possibility additionally to compare the detailed model. This is the first objective of the study and also of my presentation. The second one is to show, okay, we do see and we notice that it's actually quite demanding to accurately predict those phenomena using the detailed mechanisms. But if it is possible to get a reduced model, an optimal model that will give us not only the properties of the mixture composition, but also how it reacts, and this is we suggest within so-called global quasi-linearization approach. That is possible for like on top of that we get, and also we study the internal dimension of the system. It means that how many parameters actually needed to be integrated in time and in space to address this phenomenon. As basics, we take those, as I said, 6, and actually we take 5 mechanisms, initially 6 mechanisms, but GRI 30 wasn't included in the paper because the reviewers argues that the GRI was developed for the methane, therefore to use it for pure hydrogen mixtures is not fair comparison, and indeed it is outlier, it just produces some strange result for the high pressure. Therefore we concentrated on the 5 other mechanisms. All they have the same number, like the same number of species, the same species are involved. What is different? They participate in some group of reaction is the same, although have different parameters, but the most different, the differences on the side of the chemical reactions, and because the same species are involved, we are ready and we can compare also in a state space the dynamic of the system in a state space. It is actually what is very important for our study. The next slide shows the 10th one shows the painting of Luigi Catani. That is like I would use it as a metaphor for the system dynamics or for the model reduction we use, where we see this tower and people that throwing the stone from the tower that is hit the ground, and then probably if there is an uphill, it gets uphill and then goes to the equilibrium where the mass forces are equilibrate with the reaction of the soil. So this is like what we are also going to discover and find out in the chemical reacting system, because if you do have many chemical reaction involved, and we know that from thermodynamics that due to the chemical reaction the system goes and reaches the equilibrium. And this, what in typical application, it should be just one stable equilibrium for the all positive concentrations and so on and so forth. That is actually guaranteed by accurate modeling of those reactions. But if there are many reactions involved, then we have a force of the chemical reaction that being perturbed the system, it gets and relaxes back towards the equilibrium. It reaches the equilibrium, and because of the different forces involved and having different characteristic time scales, we do have kind of synchronization, and we have differences in the motions. Like we do have some reaction, they're more powerful and they govern the fast relaxation, and those structures, the time scale decomposition structures, induces within the system state space some kind of reduced spaces or reduced manifold low-dimensional structures that actually can be used to accurately describe the system. The next slide shows this structure for the methane model. Could you show that? The 11th one? Yes, we do see now the three-dimensional projections shown in the specific mole numbers, but not for the hydrogen system, for the methane era, because we are able here in this case to get even two and three-dimensional two-dimensional surface, three-dimensional manifold that might be used to accurately catch how the system relaxes from the arbitrary perturbed states. We see here at the magenta line, and then they merge. They go to two-dimensional surface within this sometimes three-dimensional break structure, and then they goes and merge to one-dimensional, and finally lands to the equilibrium. So far we are from the equilibrium, more dynamics involved. The closer we to the equilibrium, less dimensions actually inactive, and this structure is suggested to be investigated detailedly and suggested to be used to reduce the model. So the next slide shows the 12th one, how it can be and what was suggested to study that in depth and accurately. We look at some linearization of the source term, that is f on all those parameters. We find out the characteristic timescales we can attribute so many characteristic timescale as the degrees of freedom in our system they are, and we can sort out what are the characteristics, what are the processes, and how, and we can deal and we can handle those processes proceeding at different characteristic time in a different way. One of the obvious assumption that is actually close to the quasi-steady state assumption, if you know, it is just to keep those processes that run at very fast time as quasi-equilibrated. And this governs, and this leads us to the algebraic equation describing those surfaces presented here. This is the algebraic constraints that system during the evolution should always pertain, because those are fast the base, like a basis for the invariant subspace of those linearization matrix. Those processes should be equilibrated. If we just make a perturbation, the system relaxed very fast back to those attracting low-dimensional structures in the state space, and then we use them to integrate, and we constrain the system on those surfaces, and we look whether those constrained manifolds are enough and how many dimensions should be included, and so on and so forth, to address the phenomena in this specific case, the transition and neutral stability, or the stability problem of the rich hydrogen flame, but in overall we can implement it for any configuration, for any problem setup. So the next, this is the next one, please. This settings. Yes, how it is done. So we do not have a closed system. We are actually, after we decouple the characteristic timescales, we do have two kind of processes that is shown on the bottom line. We have a slow processes that actually needed to be integrated as it is shown here in time, right? And we have those algebraic constraints. Using this mass matrix, it is called mass matrix in the computational analysis. That is actually singular matrix, what is shown here on the bottom line on the right-hand side. We just pre-multiply the singular matrix with the time derivative, and we'll implicitly constrain the system evolving on those manifolds, like having completely constrained the system on those structures, and we then integrate it in the whole state space, but the system will always be constrained to the manifold. So the next slide shows the already some test or preliminary results what we had. Yes, and this is how it is done if we do have not only the homogeneous system. As I said, this is the homogeneous part of this is a source term. The second term in the equation using the same mass matrix would be the convection and the diffusion. So within the same matrix, within the same implicit framework, we can handle also the partial differential equation system, and the whole system will be constrained to the low dimensional manifold, and in that case we reduce, or at least we say the degrees of freedom will be equal to the dimension of those manifolds. Next, please. So what the preliminary results? So we take those linearization concept. We consider the only one mechanism, Barnard's mechanism, for the equivalence ratio for the stoichiometric and for the reach that is coincides with our internal example that we use for the detailed modeling, and we get this matrix of the bases for those processes that runs fast and should be equilibrated, and those that need to be integrated. Implicitly, we use these matrices, two matrices, and we calculated the neutral stability boundary, the critical pressure, the position of the critical pressure when the bifurcation appears. The detailed model, this is solid fat line result. Then this the first one that is a bit far away, it is like 4. The critical pressure for this considered mechanism is about 4. We have 3.6 and so on for the first stoichiometric linearization based matrix, and we have substantially improved result for the second. If we employ for the same mixture composition, we get the basis, and we can use this basis to integrate the system reduced. I forgot to mention, I also forgot to write, that the 4-dimensional manifold was identified. That is enough to address the ignition problem, and also enough 4-dimensional manifold. It means that 4 parameters are only needed to address accurately within about 5% accuracy the neutral stability boundary that is actually within the experimental accuracy as well. So the pretty nice comparison was observed. The next one, please, the 16th slide. And it actually also works within wide range of the equivalence ratio. Let's say it was from 4 to 6 is shown, but we can go further, I would guess. It's also for this very fat, it wouldn't be actually burning. But if you see this neutral stability boundary between on the bottom, we see the steady flame front. If we cross this over the pressure, for instance, change, then we see no oscillations like the oscillatory. Please rate the quality of communication. Okay, I should do it later. So the flame oscillates. As we see, this linearization concept that implemented for the stoichiometric is off. Yes, it's about 10% error, but the second one that was actually tuned or implemented for the same mixture composition, it gets very reasonable result for the neutral stability boundary. This is very exciting, and what is most important, what is more interesting, please show the next one. The 7th, yes, it is a scatter that we get for different mechanisms. Now we take the same mass matrix. It means that the bases are taken and tuned for the Barnards, for only one Barnard. This is the last mechanism here. And we use this one and calculate 2 those linearization matrices, and we calculate the neutral or like critical pressures for other mechanisms. And what we see on the left, for instance, they scatter from 4 bars for the Barnards to the 9 bars to the, what it was, this sign for the Keromnes mechanisms. It means that about 120% error between the detailed models. So what we are talking about, we do have now a detailed model. We implemented that, and we see they predict the critical pressure and varies of about 100% error. So if we use the concept of model reduction suggested, we are within up to 10%, but even if it is like considered for the same mixture, we are about 5% error, as it is shown on the next slide. Next slide, please. So this is what is shown here, even with the errors, and we see that because the linearization concept was implemented for the Barnards, it gives us the the less errors for the linearization, about 2%. But what is more important, that the same linearization, same basis was implemented for other mechanisms, having different reactions, different parameters of some reactions, of similar reaction, for instance, but still those invariant subspaces we identify, they work quite good also for other mechanisms, and as it's shown here, in spite of the scatter and difference between the detailed models, the reduced one, they are, in comparison to the range of the results of detailed model, quite close to ones that were used as a basis. As I see the first one, this is in the result of the GRI that is not shown in the previous one, and you see it is really outlier, generates about 2.5 critical pressure. That is actually off the range, and also off the range of the experimental result. So this is what about the accuracy of the reduced model, and the next slide shows, the next one. We're already about to conclude because I see probably I take too much time. The conclusions are actually very obvious. So what we what we can confirm that using this phenomena in thermal diffusion instabilities, we can definitely verify find additional parameters to verify the detailed model, to improve the performance of even for the hydrogen mechanism, improve its performance for the transient behavior at high pressures, for instance. We find out that the 4 dimensions, like a real, like an ideal model with only 4 parameters needed actually to describe ignition as well as the hydrogen air transient system behavior. And the next one, that the linearization concept we suggest, it identifies the invariant properties of the system. It is not related already to different mechanisms because it is universally applicable for every mechanisms, and therefore it describes some real invariant properties of the mixture. Moreover, the results what we see, the scatter between the different detailed models are about 100%, although the accuracy of the single reduced model implemented in the implicit form about 5–10% errors. And last one, please. Could you show the 20th one? Thank you very much. So this, what I already said, that if we tune the linearization concept, having the same, addressing the same mixture composition, we can reduce the error for about 5%. So this, we can conclude that the concept actually can be used for the parameter study, and also to develop further the closed system that will involve only 4 parameters to address the whole range of the system dynamics for the hydrogen system, and to get, like, to merge, to find out what is actually in common for different detailed model, and to get really invariant properties of the system, and then merge and develop the mechanism that would be the best from the existing ones, let's say. So the bottom line, what is the most important, like a message that you should take home, actually, it is like we demonstrated that this reduced modeling is applicable for different kind of the flame propagation phenomena, but it also the phenomena itself might be used to address and to verify and validate additionally detailed chemical reaction kinetics. So by that, I would like to in my talk, and the financial support of the joint project with myself and Vladimir Gubernov involved, of the German fund for the basic research, for the fundamental research, and also Russian fund for the basic research. Those are numbers of the grant that the financial support is acknowledged. Now I would like to take my question, although probably we are not, like, I'm sorry for the time management because of those slides and so on. Thank you very much for your attention.
Thank you very much, Dr. Bykov, for excellent presentation. It was very interesting, it's very stylish and very clear. We don't have questions on our chat, but I want to ask one question.
Yes, please go ahead.
I'm sorry. We have one question in question section. I will voice it. Thank you for interesting presentation. The question is: did you estimate the reduction of computational cost by using your reduced chemistry mechanism instead of commonly used ones, for example, GRI3 mechanism?
Yeah, very nice. It's like I would say, killing question for us at the moment, because what I've shown how to constrain the system on the 4 dimensions, like 4 parameters are integrated really in time and space, but they are implicitly handled. It means that all those mass matrices and within the method of lines implementing method, we integrate not the reduced one, we integrate the whole system being constrained on the 4-dimensional manifold. It leads to the fact that having integrated the differential algebraic system, it is known phenomenon, it's more demanding as to integrate only differential equations. Therefore, at the moment, it's not like I wouldn't suggest that really to implement as a reduction concept. So at the moment, it is a framework to test whether those 4-dimensional manifold or those constraints, they might be and how they proper or they are not proper address the phenomena. So when we are like at the moment, at this stage of the investigation, we see that those constraints we identify, they perfectly address whatever we need to be modeled or whenever need to be modeled. But now, the next question, how to get those constraints, those algebraic equations, and to simplify them, and what concept to be used such that we get a closed system only having 4 parameters. And then if we have a 4 parameters, it would be like a very simple task to compare. You integrate 4 scalars or you integrate 11 scalars. Typically, to integrate the algebraic, the complexity of the integration would be as dimension in square, right? So then you can compare, like having 10 species, you would like something, the number of your operation would be proportional to something multiplied with 100, or having just 4 species, and then you should multiply it with 16. It will be 5 at about 5 to 10 times more efficient within the integration. So we have for some certain 2-dimensional reduced model, we have a tabulation concept that really shows this factor of 1 order or 5 times at least at most, or at least they're safe in the computational time. So this, I hope partly I answered the question.
Okay, thank you very much for your answer. And I want to ask a very little question. Does rotational behavior of flame speed from some critical pressure value takes place for methane air mixtures? If yes, what is the value of critical pressure and what is the equivalence ratio?
So for the methane, I'm not sure, because we need to generate quite a high Lewis number. So therefore the hydrogen is the substance is very small. The Lewis number for the rich mixture get huge. But if we dilute it with something, there probably would be similar phenomena appears. So I'm not familiar with that. So I would say several papers were referenced, and one of them there are some attempt to what kind of, I don't know, butanol, whatever it was. It was some attempt to get experimental result and to get wide range of system to observe that phenomena. But well, I was specified on the hydrogen, therefore I didn't look at in detail for more detailed mechanism. We are just trying to get the basic result on the simplest one, and then we will be extended. But the extension is just will be more or less algorithmically seen. Should be automatic. Should be some substantial difficulties to extend it to more complicated fields. Just
Okay,
look at
thank
the
you very much.
references around, yes.
Okay, thank you.
Yes, we plan to do that for the lean methane air with the hydrogen addition, yes. I see the question of Anatoly Masnoy, and he asked about the lean methane air. Yes, we plan to dilute it also methane with the hydrogen, because right now it is a trend to get like access of electricity to transfer that to the hydrogen and add to the fuels, and just to reduce some, I don't know, to reduce the exhaust and so on and so forth. Therefore, methane hydrogen mixtures, they would be prone to such a phenomenon, because we do have a hydrogen content or like addition to that. Yes. So it would be the next step.
Thank you very much. We should following the schedule, and
yes. Sorry again for my
the next will be made by me, and combustion wave propagation, local phenomena. First of all, let's consider the combustion wave within porous media. A combustible mixture filtrates through the matrix where exothermal reaction occurs. During the process, a specific wave-shaped thermal structure forms as a result of intense heat transfer between the fluid and solid phases. The heat released due to chemical reaction transfers to the preheating region via thermal conductivity of the porous matrix and radiation. Such wave can be steady state or propagates in upstream or downstream direction, depending on flow velocity, mixture composition, and properties of solid structure. In our work, we consider the process at pore scale. We explicitly simulated the fluid flow in interstitial space reactions, interface heat transfer, solid thermal conductivity, and radiation. It is obvious that there are two methods of geometry generation. Synthetical approach for packet beds of particles using discrete element method, and reconstruction for foam-like structures using X-ray computer tomography. We used both of these approaches for packet bed of ceramic spheres and for porous emitter made by self-propagating high-temperature synthesis. Right picture. As a result, on this slide, the three-dimensional distribution of major process parameters over the porous matrix and the interstitial space are presented. The region of mixture preheating, region of heat release rate, and the thermal relaxation can be observed here obviously. It can be noticed that irregularity of the porous structure has a significant impact on the flow distribution of the local parameters. In figure G, the region of intense heat release is shown. it can be seen that the flame front has a non-planar shape and remains a cellular structure. Zones of maximal heat release rate are located within cavities where the flow is developed. Let's consider the temperature field more precisely. As the cross-section, we can see that fluid and solid temperatures are not equal. Indeed, in preheating region, the temperature of porous matrix is higher. Sections 1 to 4. Conversely, after heat release region, section 5 and 6, the fluid temperature is higher. Such thermal non-equilibrium is a result of heat recuperation mechanism. On this slide, the fluid and solid temperature profiles are shown in comparison with experimental data. Our numerical results are depicted by solid lines, while the experimental data by connected dots. Large thermal non-equilibrium near the heat release region was predicted also. Let's consider the difference between heat transfer intensity for lean and ultra-rich mixture compositions. Small excess of oxidizer led to larger heat release rate in comparison with rich mixture composition. Here we observe a steeper thermal gradient near the flame front, as well as magnitude of interface and radiative heat transfer fluxes. Hence, in general, the structure of heat transfer is similar for both cases. On this slide, we can consider the heat transfer structure more precisely. Indeed, the fluid-solid heat flux is strongly with heat release rate region, and the heat recuperation mechanism is very clear here. Before the ignition point, the flux is directed from the solid matrix to the fluid and vice versa. The structure of radiator head flux is more complex, and let's take a look at the picture C. The energy is transferred through the bed via radiation, layer by layer, due to restricted mutual visibility of the opaque particles. We also regarded unsteady phenomena also. Unfortunately, we have only PDF version of presentation, and maybe I will try and share my screen to show the animation. Okay, fine. We can see the animation, and here you can see the flame front propagation through the bed for lean and rich mixtures. In contrast to the volume average approach and volume average models, the large spatial and temporal variation of the flame front can be observed. The different flame fragments propagate with different velocity depending on the local porous and flow structure. Previous slide demonstrated quasi-steady macroscopic combustion wave propagation, but there is certain critical value of flow velocity below which an instability phenomena take place. This form of instability is known as a flame with repetitive extinction and ignition, so-called fray. It consisted of the following repetitive stages: flame ignition, upstream flame propagation, until the local critical diameter becomes greater than pore or channel diameter, extinction of the flame in this region, transportation of the combustible gas mixture to the position of ignition, and so on. Right figure demonstrates results of two-dimensional simulation in a regular analogy of packet bed, two-dimensional. Left result is the simulation in a three-dimensional statement in irregular packet bed. This picture in some center section of this model. And I also want to show very briefly some results of per-scale simulation of the radiant burners. I mean cylindrical annual radiant burners. And we also used per-scale approach to simulate the combustion in this system. And we discovered three characteristics regimes of combustion based on the flame position and the heat equilibration phenomena. We can see this mode on this slide more precisely. And in low flow velocity, we have internal mode under which the front locates in central cavity of the burner. Moderate flow result in submerged flame, and large flow velocity leads to surface stabilized flame. And the picture in the bottom of slide, you can see that how flame front deforms during increasing of the flow rate. During the simulation, we compared our numerical results with experimental observation qualitatively, and we detected that such flame structure can be formed also during experimental tests. So it's time to finish my speech, and major conclusions were declared during my talk. You can see it on the slide. Thank you for your attention, and I can ask you questions if you have. We have questions. You are talking about numerical modeling. What kind of mathematical model was taken as a basis? What assumptions? It is complex questions, and to be briefly, I can say that we used standard CFD numerical model based on Navier-Stokes equations that describes a flow field within interstitial space, and we also calculated the conductive heat transfer within solid structure using a famous equation. And we also used detailed chemical mechanism, I mean GRI-3 mechanism for simulation of chemical processes. And what about assumptions? I think that the most important assumption that we used is a diabetical approach, that we didn't use some models for heat losses, and we all understand that this phenomenon of heat losses can change the results in context within the context of precise data of flame propagation velocity and maximum temperature. And maybe this is a reason that we have some difference between experimental and numerical data. And also, this was very important that we didn't take into account that from free surface of packet bed, we didn't consider the radiative heat losses from that free surface. And of course, it's also can be very important, but our approach is very expensive in terms of computational cost, and maybe in further work we will consider that phenomenon. What software was employed? We used ANSYS Fluent as a basic software, but some submodels were implemented on that code using function of user-defined function customization tool that is based on C language tools. Okay, thank you very much, and now it's time to hear the next presentation that will be made by Sergey Zambalov.
Hello, dear colleagues. My name is Sergey Zambalov. My presentation devoted to numerical simulation of the range extender with hydrogen multiple fuel injection system. Okay, so let's begin. Okay. I have some technical problems. I'm sorry. With the slide change. The automotive industry is one of the largest contributors to greenhouse gases. According to the International Energy Agency, the transport sector is responsible for 1/3 of the world emission. In turn, emission from on-road vehicles reach 70%. Okay, the next slide, please. One of the possibilities to reduce emission can be use of the electric individual transport. The limitation of the driving range is the main problem of electric vehicles. Introduction of a small power unit, also known as a range extender, that recharge batteries is one of the possible solutions for the short range problem. Okay, next slide, please. The range extender converts the chemical energy of the fuel to electricity. The power unit usually includes a combination of internal combustion engine with an electric generator. New technologies like fuel cells and microturbine have the potential to replace the internal combustion engine, but remain very expensive. The one-kill engine is well suited for the range expansion due to compact package, large specific power, low weight, noise, and vibration. Okay, next slide. The research object is the single-section rotary engine. The rotation of triangular rotor in engine was investigated because of the symmetrical structure. Okay, next slide. The simulated engine has side-ported intake and exhaust manifolds. the hydrogen fuel is directly injected into the combustion chamber. The engine has two ignition spark plugs, the leading spark plugs and the trailing spark plugs. The operation parameters of the engine are presented at the table. Okay, next slide, please. The multiple injection system can split the process of the fuel injection and change pressure, duration, and the timing of the pulses. In this study, three different cases were considered. Case A is a standard single injection process. Case B and C include 2 and 3 equal injection peaks accordingly. Okay, next slide, please. Based on the evolution of the hydrogen mole fraction, the cases under multiple injection strategy, cases B and C, have additional peaks that corresponds with the injection pulses, while case A remains uniform. At the late stages of the induction cycle, the difference between the cases become minimal. The multiple injection system affects the air induction process. The local fluctuations are the result of the hydrogen injection that put resistance in the way of air induction. Next slide, please. The evolution of the major parameters such as the pressure, hydrogen consumption, heat release rate, and total area of the flame front are shown for each case. The existence of the special points can be observed. They can be caused by the flame front formation from the leading and the trailing spark plugs, propagation of the flame front, merging and extinguishing while reaching the chamber's wall. The analysis of the combustion stroke showed that the injection strategy have significantly influenced the combustion process. Next slide, please. Different injection strategies result in a different distribution of the local turbulent parameters and local equivalent ratios that directly influences the local effective flame speed. The green line shows the position of the flame front after 3 degrees of the rotation of the crankshaft. This one. The nitrogen oxide formation analysis showed that the fuel stratification influences the pollutant formation significantly. Different injection strategies result in variation of the nitrogen oxide emission up to 2 times. Okay, next slide. According to the performance parameters tables, the indicated parameter power target for range extender at 20 kilowatts are achieved for all cases. Based on performance characteristics of the proposed range extender, the comparison between the range extender solution was made. The majority of the range extender prototypes employ piston engines fueled by gasoline. The presented rotary range extender prototype not only has a higher value of the power per unit volume, but also can provide lower level of nitrogen oxide emission. Okay, it's time to finish my speech. Thank you for your attention. Ready to answer your questions.
Thank you very much, Sergey, for your excellent presentation. And we have one question from Anatoly Masnoy. Thank you for interesting presentation. My question is, what is the mechanism was used for modeling nitrogen oxides chemistry? You mentioned notable reduction of emission. Why the emission so reduced?
Okay, thanks for the question, Anatoly. The chemical mechanism is include 40 species and 250 reaction, and this mechanism is based on the mechanisms of hydrogen combustion proposed by Conair, which is include 10 species and 40 reactions. The second question is about reduction of the NOx emission. We think that the multiple injection system significantly results in this because it results in a different distribution of the local equivalence ratio and provide such as a distribution of the hydrogen that can increase the hydrogen combustion and increase which can result in the reducing in NOx emission. Okay.
Thank you, Sergey, for your answer. And unfortunately, we have only 3 talks on this day, and we should finish our session today. And I want to remember that if someone has additional questions, one can use the forum of our Congress to ask it. I'm sure that all participants will answer it later. And tomorrow we will continue. We will continue our section, and I hope that all participants will be so interesting as this day. And thank you very much for your talks, and let's continue.